Welcome to the second episode of our course. In the previous episode, we covered how to set up the working environment and establish communication between the ECS control center system and a simulated PLC controller. Now it's time to move on to more practical topics. We will program our first automation system. In this episode, we will focus on the following ECS system components: Unimotor, motor configuration and control; Interlock, system safety interlocks; Analog, processing and handling of analog signals; Alarm, alarm management and handling. The goal of this episode is to build practical skills by programming a simple automation system using these components. Before we start the implementation, we will first thoroughly explain how our automation system should operate. This will give us a clear understanding of the system's functionality and a vision of the outcome we aim to achieve during the creation process. The first project presented in this course will focus on a coal transportation system. The system will consist of two silos, two analog measurements to determine the percentage fill level of the silos, overflow sensors, and 3 screw conveyors. For conveyor systems, the sequence of activation is crucial. The system should be activated starting with the last conveyor and moving in reverse order to the first to prevent material overflow. For example, if the first conveyor is activated before the second, material would accumulate at the transfer point, potentially causing a blockage. Similarly, when shutting down the system, the sequence should be reversed, starting with the first conveyor and finishing with the last. This prevents a situation where an earlier conveyor remains running while the next one has stopped. This functionality is typically managed using interlocks. For instance, if the second conveyor fails, the previous one should also stop. This project would involve a single group that can be selected and then started. Upon starting the group, icons representing sirens will indicate that the group is in the process of starting. As expected, the conveyors will start in reverse order, from the last to the first. Next, we'll see how the system reacts when the second conveyor fails. We observe that triggering an overload signal on the second conveyor also stops the first conveyor. To resolve this situation, the motor protection switch must first be reset, and then the alarm must be acknowledged. Once the alarm is acknowledged, the group can be started again, which will restart conveyors 2 and 1. Let's move on to the implementation. The first step will be to create a new screen where we will display our visualization. To do this, go to the Visualization server and click on the System tab. Then expand the Configuration section and select HMI Editor. Click the New button and choose the screen resolution for our visualization. In my case, the resolution is 1920 by 1200, so I select New Mimic. Target screen size 1920 by 1200. Keep in mind that all elements created in this project need to be assigned to one solution, including our new screen. From the drop-down menu, select Solution A1, which we created in the previous session, and then click Save As. Name the screen. I'll call mine S1A1M01 and click OK. Now you can see that our Mimic has a name, and in square brackets, it shows that it belongs to Solution A1. Next, let's sketch out our system. First, we'll set the background to make it easier to work with the elements. Click on Background and choose HMI Background, Point Grid. Now we'll add 2 silos and 3 screw conveyors. Open the toolbox, and to add silos, select Static Part, type Top, and choose a silo named Silo Cut Section Top. To modify the appearance of the top part of the silo, click on it and check the Splitter option. You can also enlarge the silo slightly to better fit our system design. Since there may be multiple silos on a site, they are usually named accordingly. We'll name our silos Silo 1 and Silo 2. To do this, expand the additional options by clicking the arrow, select Shapes, and then Label. In the text field, enter Silo 1. To center the label, go to Label Content Alignment and set both vertical center and horizontal center. In the Text Attributes section, we can also change the text color. In ECS, the standard color for labels can be selected by expanding Text Color, choosing Global Color, and selecting Static Text General. If we find it difficult to precisely position the text in the center, we can increase the grid density by clicking Grid Size and setting it to a smaller value. This will allow for more accurate placement of elements. Next, click and drag to select the silo along with its label, and then copy it using Ctrl-C and Ctrl-V. On the copied silo, rename it to Silo 2. The next step is to add 3 screw conveyors. Open the toolbox, choose Dynamic Symbol, and search for an element called Screw Conveyor. Drag it onto the screen and click on it. You can modify the symbol as needed. Select top left and bottom right to adjust the graphic, which will add protrusions to the symbol. Copy this symbol twice more and arrange them to reflect the flow of material from Silo 1 to Silo 2. Finally, let's add arrows to indicate the direction of material flow. Open the Shapes menu, select Sticky Line, expand the Arrows tab, and check the arrow end box to add an arrowhead. Now tidy up the screen so it clearly shows the material flow between the elements. At this point, it's worth discussing some useful functions that the ECS system offers when arranging elements on the screen. Using the Select View button, you can zoom in on a specific section of the screen, while Zoom Out allows you to zoom out. Reset Zoom restores the default zoom level. When you want to select multiple elements at once, such as the conveyors, hold the Shift key and click on each element. You can then align them by selecting Align and Align Left, which will neatly align the conveyors to the left edge. Additionally, when you have an element selected, you can adjust its position using the arrow keys on your keyboard. This enables precise positioning of elements on the screen. As you can see, everything now looks much better. Let's save the changes by clicking the Save button. Next, go to the HMI Matrix Editor, where you can place your screens in a matrix layout. In large industrial setups, there can be dozens of screens, so it's important to keep them organized. Once again, select Solution A1. To add levels and columns to the matrix, click Add New Level, then add a column by selecting Add New Column, and a row by clicking Add Row. On the left side, you'll see a list of available mimics. Drag our mimic, S1A1M01, into the chosen cell of the matrix. Once the screen is placed, click Save Changes to apply the changes. Now navigate to the Product tab, expand ECS Control Center V9, and then Operations Station. This is the view the operator will see. When you click on Matrix, you should see the single screen that we added to the grid. To maintain order and clarity in our projects, we'll adopt a standardized naming convention for elements. This system consists of several parts, and the number of parts depends on how deeply an element is nested within the project's hierarchy. For elements within a specific group, we typically use 3 parts. The first part refers to the department in which the group containing the element resides. The second part indicates the group to which the element belongs. The third part describes the type of element. Examples of element type codes: M, motor; G, gate; V, valve; W, weight; S, select; AL, alarm; AN, analog measurement; PID, PID controller. The code A1G01 can be broken down as follows. A element belongs to department A1. G01, the element is in group G01. M01, the element is a motor labeled M01. This naming convention allows for quick identification of components, which is critical in large systems. It enables us to easily locate and manage elements within a project, facilitating its development and maintenance. In addition to the standard naming structure, we also introduce suffixes, which are added after an underscore. These suffixes provide additional details about the specific function or characteristics of an element. Let's say we want to create an interlock for a motor with the code A1G01M01. The name would be A1G01MINTL, where A1G01M01 refers to the motor. INTL is a suffix indicating this is an interlock. We can use different suffixes for various types of interlocks. Suffixes are also extremely useful for labeling analog measurements and alarms. They help quickly identify what exactly the measurement is tracking or what kind of alarm has been triggered. For example, if we want to measure the current of a motor with the code A101M01, we might label the first analog measurement as A01 and then add a suffix to describe what's being measured. For example, power, current, speed. Thus, The name A1G01M AN01 current means we are dealing with the first current measurement for motor A1G01M01. This naming convention, along with suffixes, gives us a structured and clear way to label and organize the elements in a system. It ensures quick recognition of each component's function and allows for smooth project management, especially as systems grow in complexity. I hope this gives you a solid understanding of the naming standard we'll be using throughout this course. Let's now move on to configuring the hardware of the controller on the engineering station. To do this, click on S1PLC1 and then go to the Hardware tab. As a reminder, in Rack 0 in slot 5, we have a digital input card installed. Its starting address is I0.0, and the card offers 32 digital inputs, which corresponds to 4 bytes of address space. This means that the first address of the card is I0.0 and the last address is I3.7. Similarly, in slot 6, we have a digital output card. Like the input card, it has 32 digital outputs. Its starting address is Q0.0 and the last address is Q3.7. Now, let's close the hardware configuration and move on to the symbols table, where the symbolic names for the PLC's inputs and outputs are defined. To do this, click on S1PLC1 and select the Symbols tab. This will open the Symbols table, which allows assigning descriptive names to specific input and output addresses in the system, making it easier to identify and manage them. To control the drive, we need to define the appropriate input and output signals for the PLC to be able to read the drive's status and send control signals to it. Digital inputs allow us to monitor the drive's status, while digital outputs enable its control, for example, by activating a contactor. In our example, we have reserved 8 digital inputs for the A1G01M01 drive, starting at address I1.0 and ending at I1.7. Each of these inputs corresponds to a different signal from the automation components. Below is a description of each signal for the A1G01M01 screw conveyor. I1.0, ready, drive readiness signal. It comes from the auxiliary contact of the overload relay. An active signal indicates that the overload protection has not been triggered. I1.1, overload signal. An active signal indicates that the drive is not overloaded. I1.2, return 1 feedback contactor, feedback signal from the drive contactor. An active signal indicates that the contactor has been activated. I1.3, local start direction 1, local start signal in direction 1. An active signal indicates that the start button has been pressed. I1.4, local stop, drive stop signal. An active signal indicates that the stop button has not been pressed, meaning the drive is not stopped. I1.5, remote, signal from the maintenance switch. An active signal indicates that the maintenance switch is in the on position. I1.6, safety switch, signal from the safety relay. An active signal indicates that the device is in a safe operational state. I1.7, motion detector signal. An active signal indicates that the drive shaft is rotating, confirming the movement of the drive. To control the drive, we will use one digital output, Q1.0, which will activate the contactor that starts the screw conveyor motor. Q1.0, command 1, control signal to activate the drive contactor. Now that we know which signals are coming into the PLC and which are being sent to the drive, we can move on to programming our first Unimotor. Let's now proceed to function FC4001. Right-click on it, select Object Properties, and rename the function to match our first drive. In the symbolic name field, enter A1-1FC, and in the symbol comment field, add the description, screw conveyor 1. Similarly, we change the name of the DB4001 block. In the symbolic name field, enter A1-1M1DB. Next, open function FC4001, where we can also add an appropriate comment. The program already contains a framework, which includes a network responsible for the interlock. To temporarily prevent the interlock from blocking the drive activation, we will input the always-on signal to the IN1 input. This will ensure that the interlock is always met and will not block the drive. Next, let's move to Network 4, and in the FB block, connect the physical signals we previously defined in the symbol table. RDY I1.0 drive ready signal, OVL I1.1 overload signal, RIT1 contactor feedback, LST1.3 local start direction 1, LSTP I1.4 local stop signal, RMM5 maintenance switch signal, SSW I1.6 safety switch signal, MD I1.7 motion detection signal. As the output for block CON1, connect the signal Q1.0, which will control the activation of the drive. Save the changes by clicking the disk icon or using the shortcut Ctrl+S. The next step is to configure the simulation of our drive. The simulations for individual units are located in function FC789U, so let's navigate to it. In Network 2, we can see the SimMotor function call, which handles the drive simulation. We need to connect the signals defined in the symbol table. This will allow us to overwrite physical input states with simulated signals during SCADA-level simulation. The FC block will overwrite the physical input, causing the FB block to read the simulated input state instead of the actual state on the PLC card. After connecting the signals, save the program. Next, let's move to the group function, FC1501. For now, we want this group to call only the one drive we just created. To do this, change the language to STL, and then call the function FC4001, which is the function for our drive, by entering call FC4001. Let's also enable the controller simulation. Open Net to PLC, then launch PLC Sim and load the program onto the controller. Once the program is loaded, switch the controller to run mode. After that, configure Net to PLC Sim by selecting the appropriate network card, the simulated controller's address, the rack, and the slot, then start the server. That concludes the process of adding the Unimotor to the project from the PLC side. Now, in the ECS system, we need to add a so-called point. To do this, let's switch to the ECS server. Let's first ensure that the connection between the simulated PLC and the ECS system is properly established. As we can see, the connection is active. Now, navigate to the System tab and click on Point Editor. This is where we can add new points to the ECS system. Our first task is to add a department. To do this, right-click on Alarm Route, then select New. A window for adding points will appear. First, we choose the previously created solution A1. In the Type field, we set it to Point and name the group A1. For the function parent, we leave it as Alarm Route. Next, we click on the binoculars icon to choose the point type. Type in Department and select Point Type ACESYS Department 8.0. For the I/O interface, we select Siemens. Next, click on the department we've just added to input additional data. In our case, the department is responsible for transport, so we enter transport in the description field. The most critical aspect to configure is the I/O interface. This is how the ECS system knows where in the PLC memory the data for a given point is located. First, we select the previously configured PLC S1 PLC1, then fill in the following fields. Input, type DB 32-bit, time DB1 DBW 6-bit 0, output, type DB 16-bit DB 1001 32-bit 0, parameter, DB 1001 DBW 0. After entering this information, click Save to save the configuration. You're probably wondering why the input, output, and parameter fields for Department A1 are configured this way. Let's head over to the engineering station to clarify. Open the department's function, FC101. The input field refers to the statuses that the given element sends to the ECS system, which is why these signals are considered input for ECS. Notice that the MSW pin, which sends the department status, is connected to address db1.dbx6.0. db1 is a data block that contains a table of department statuses. Let's open this block. We see that the DB contains a table of 100 structures, where each element of the table is a structure. By clicking View and then Data View, we can confirm this. For index 1 in the table, we see the status bits returned by our group. It becomes clear why we configured the input as a 32-bit DB in the configuration. We want to read exactly that many bits from this structure, 16 Boolean values and 1 integer for the status. The last element of the structure is a timestamp, which has no relevance in ECS, so we don't read it. The output field refers to the signals that ECS will send to our department in the PLC program via the operator faceplates. Let's return to FC101 for a moment. As we can see, the department's function block is assigned DB001. Let's open this data block. Inside, we find a structure called FPCMD, which is responsible for sending commands from the ECS faceplates. This means that when we press Start from the department's operator panel, ECS will link that command to this block structure and send a signal to address 33.2 in DB1001. We set the type to 16 bits in the configuration because we only want to read exactly 16 bits of data. Finally, the parameter field refers to parameters that we can provide to our department from the ECS system, such as timings or other configuration parameters. In our case, it will always be the data block number linked to the function block call for the given element. In a similar manner, other points such as groups, unimotors, alarms, and analogs are added. Let's summarize what has been said. In the ECS system, when adding a new point, we need to define 3 main memory areas. Each of these areas plays a distinct role in managing data between the controller and the ECS system. The first area, input, refers to statuses that the point sends from the controller to the ECS system. These statuses are stored in memory blocks that contain arrays of structures representing the status information. The second area, output, is associated with signals sent from the ECS system, such as commands. An example would be activating a drive by pressing the Start button on the faceplate. These signals are stored in the data blocks of the specific point instance and can be found under the variable FPCMD. The last area, parameters, is used for parameterizing the object. This includes settings like timing, scaling, and other configuration parameters for the point. To streamline the process of adding new points, an addressing table has been prepared. This table allows for quick and standardized memory address assignments based on the point type, eliminating the need to manually check addresses each time. It also introduces a convention for numbering function blocks, FC, and data blocks, DB, within the system. For example, departments are assigned function and data block numbers from 1001 to 1100, while groups start from 1501 to 2000. To understand how to use this table, let's calculate the addressing for a department that has just been added to the system. Since this is the first department, its number is 1. Therefore, both the function block, FC, and the data block DB are numbered 1001. By applying the relevant formula, we get the following addresses. Input, DB32-bit time, DB1 DW6-bit 0. Output, DB1001, DW32-bit 0 parameter, DB1001. As we can see, this addressing matches what was set for the first department point. The table allows us to easily assign memory addresses for additional points, greatly simplifying the process. For Group 1, which we are about to add to the ECS system, we apply similar principles as for adding a department. According to the numbering convention, the function block for Group 1 should have the number 5001, and the data block, DB, should also be numbered 1501. After applying the value of 1 to the relevant fields in the table, we arrive at the following addressing for Group 1. Input, DB32-bit, time DB2 DB6-bit 0. Output, DB1501, DB44-bit 0. Parameter, DB1501. These values show how to correctly configure the first point for a group in the ECS system, following the established table. Let's move on to the ECS system and add the next points. First, we will add the group for which we just calculated the addressing, and then we'll proceed to add our first motor. Since the group is part of a department in the hierarchy structure, we begin by clicking on Department A1 and selecting the New option to add a new point. We make sure the correct solution, A1, is selected, and name the group A1G01. Next, we select the point type as point type ACESYS Group 8.0 and set the I/O interface to SIM since we are working with a simulated Siemens controller. In the description field, we enter coal transport because this group will be responsible for transporting coal from Silo 1 to Silo 2. Finally, we input the previously calculated addressing, and once everything is set correctly, we save the changes. In this group, A1G01, we will place our first motor, A1G01M01. This is a so-called Unimotor, meaning it can only move in one direction. Since the motor is part of this group in the hierarchy, we click on the newly created group and press New to add a new motor. We ensure we are still working in solution A1, name the motor A1G01M01, and select the point type as point type ACESYS Unit Unimotor 8.0. We set the I/O interface to SIM and click OK. The next step is to assign the motor the name Screw Conveyor 1. Then, we input the appropriate addresses we previously calculated for this motor. This is a great opportunity for you to verify your understanding of how to use the address table. Try calculating the addresses for the Unimotor yourself and compare them with those we've entered. After saving the changes, our hierarchy in the ECS system now looks like this. A1, department, with the following structure below it. A1G01 group, containing one motor, A1G011 motor. Let's refresh the changes by pressing the F5 key. Next, open the HMI editor and select the previously created screen by clicking Open and choosing S1A1M01. At this point, let's place the previously prepared points on the screen, starting with the group and drive points. Click on Tag Browser, and then drag the group A1G01 and drive A1G01M01 onto the screen. As you can see, the system automatically adds the default symbol for each point when dragged. Since the drive we added is a screw conveyor, we will copy its tag name and paste it under the first conveyor. Then, remove the drive symbol. To improve the readability of the screen, it is worth organizing the elements. If there are many drives in the system, it's best to label each with a unique name. To do this, go to the toolbox, select Dynamic, and drag the tag name display onto the screen. Assign the name according to the drive's tag name and link it to the appropriate tag. You can also reduce the font size, for example, to 12. Click Save to save the changes, and then Preview to see how the screen will look from the operator's perspective. Double-clicking on the group will open the faceplate from which you can control the group. In the Control tab, under the Start-Stop section, you will find buttons for group control. To start the group, first select it by clicking the Select button. All drives within that group will be highlighted in white, indicating to the operator that they are ready to be started. Pressing the Start button will start the group. When you want to stop the group, first click Deselect and then Stop to shut down the drives according to the shutdown sequence. There is also an option for immediate stop using the Quick Stop button, which will immediately stop all drives without delay. Let's now test the simulation. Click on the drive, then go to the Dev Sim tab, where you can simulate input signals. For example, when the drive is running, a confirmation signal is received from the RET1 contactor. Now let's simulate pressing the emergency stop button. Checking the checkbox means the signal has a logical value of 1, as if a 24-volt signal is being sent to the PLC's digital input. Unchecking the SSW safety switch will turn off the drive and trigger an alarm. To acknowledge the alarm, right-click on the alarm bar and select Acknowledge, the bell icon. Simulation plays a crucial role in testing complex sequences and ensuring that the system operates as intended. It allows us to safely test various scenarios and confirm that everything functions correctly. Let's now move to the engineering station to review how the A1G01M1 drive is controlled by the A1G01 group. First, open the group function FC-FITS01 and scroll down. You'll see that the function block for the group has two key outputs, command and token. These two signals need to be connected to the drive for control to be possible. When we click Start on the group's faceplate, the function block generates the appropriate command in the CEMD structure, responsible for issuing the start command. Any drive that has the CMD signal from the group connected to its input will receive the start command and initiate the startup procedure. To confirm this, let's open the function FC4001 for our drive and ensure the signals are correctly assigned. As we can see, the CMD input of the drive's function block is connected to the CMD signal from the A1G01 group. Similarly, the token input is connected to the token from the same group. The key takeaway is that if we want to link a drive to a specific group, we must connect the CMD and token signals from the group to the drive. Now, let's move on to creating two additional drive points, A1G01M02 and A1G01M03. We will do this by copying the existing function FC4001 for the drive A1G01M01. To do this, right-click on the FC4001 block, select Copy, then right-click again and select Paste. After pasting, click Rename and assign the next function number, which is 4002. Similarly, add function FC4003 for the drive A1G01M03. Make sure to properly name the function in Object Properties and add an appropriate comment describing the function. After these steps, we also need to copy the corresponding data blocks DB for our drives. Copy DB4001 and create new data blocks DB4002 and DB4003, giving them the correct names. Next, open function FC4002 and rename it. To quickly replace all references to the data blocks, press Ctrl F and use the Find and Replace option to replace all occurrences of A1G01-1DDB with A1G01M02DB. Select the All option to apply the changes throughout and then click Replace All. The next step is to update the physical input connections. Assume that A1G01-02 has the same signals, but they connect to different digital inputs, starting from I2.0. After updating the inputs, you also need to change the MSW output index. This index is used to send status information to the ECS system, so it must be unique for each drive. For the second drive, we will set the index to 2. Then, update the digital output to Q20. Perform the same steps for function FC4003, thereby creating the drive A1G01M03. Next, let's set up the simulation. Go to function FC7990, copy the second network, and rename it. The quickest way to connect the simulation is to use Ctrl F again to replace all references to A1G01M01 with A1G01M02. By following proper naming conventions, we can quickly implement all the necessary changes. Repeat the same procedure for the drive A1G01M03. After creating the simulation, we need to call the new drives in function F1501 by adding call FC4002 and call FC4003. The final step at the engineering station is to load all the modified functions and blocks. Hold Ctrl and select the group function F1501, functions FC402 and FC403, data blocks DB402 and DB403, and the simulation function FC7990. Finally, click the Download button to upload the changes to the system. Let's now proceed to the server. Open the point editor and add the two drives we previously created, A1G01M02 and A1G01M03. We will add them in the same way as the previously added drive A1G01M1 to the group A1G01. We assign appropriate names to the drives and specify the memory areas in the controller to which each point should refer. Once this is done, we move to the HMI Editor tab and open our screen. We assign the correct names to the new screw conveyors as they were defined in the program and connect the relevant symbols to the corresponding tags. After completing this, we save the changes and click the Preview button to open the operator window. The first thing we need to do is set non-zero timers for the drives. If the time is set to 0, the simulation will not have enough time to return the appropriate signals before the ECS system generates an error. Therefore, we navigate to the Timer tab and enter the appropriate time values. Now let's test whether the group functions properly. We select the group, click Select, and then Start. As we can see, the group starts and operates correctly. However, currently, all conveyors start simultaneously, which could be dangerous. A better approach would be for the conveyors to start in a specific sequence. During startup, A1G01N03 should start first, followed by A1G01M02, and finally A1G01M01. When shutting down, it should happen in reverse order. A1G01M01 stops first, followed by A1G01M02, and lastly, A1G01M03. The best way to implement such sequences is by using interlocks. Interlocks not only allow drives to be started and stopped in a specific order, but also ensure the safety of the system. If one of the conveyors fails, the interlock will automatically disable the relevant drives, as the condition for starting them will not be met. At this point, let's notice that if the middle conveyor fails, for example, due to overload, A1G01M01 will continue to operate. This is a potentially dangerous situation, as the material will accumulate at the transfer point between A1G01M01 and A1G01M02, since the damaged conveyor will not be able to move the material. This could lead to a blockage, risking system damage or even failure of the entire process. Let's shut down the group and implement interlock functionality for our system. Before we proceed with implementing the interlocks, it's important to first understand how they function. Similar to other system elements, the interlock function returns its status via the MSW, most significant word structure. The statuses of all interlocks are stored in the DB10 data block, which contains an array of interlock status structures. A key aspect is ensuring that each interlock has a unique index in this array, as this guarantees proper system functionality. To maintain this uniqueness and order, we will adopt a specific naming convention for interlocks in our project. The interlock number will consist of 4 digits. The first digit represents the department number. The second digit is the group number. The third digit corresponds to the unit number the interlock is assigned to. The final digit is the interlock number within that particular unit. Interlocks are linked to a specific element through the function block input called link. There are 3 types of interlocks you can link to an element: interlock, sequence start interlock, SE start INTL, sequence stop interlock, SE stop INTL. The type of interlock used depends on what you aim to achieve. For the INTL interlock, if it is not met, the entire group cannot start. If this interlock is triggered while the group is running, it will immediately stop the whole group. This type of interlock is typically used for emergency situations, such as pressing an emergency stop button, pulling a safety cable, or overflow in a tank. In such cases, the group must be stopped immediately. The sequence start interlock works slightly differently. If this interlock is not fulfilled, the group can still start, but the specific drives for which the interlock condition is not met will not turn on until the interlock condition is satisfied. If the drive is already running and the sequence start interlock is triggered, only that specific drive will stop, while the rest of the drives in the group will continue to operate. Similarly, the sequence stop interlock functions during the shutdown process. When the group is commanded to stop, the drives with active sequence stop interlocks will not shut down until their interlock conditions are fulfilled. Sequence start and stop interlocks are typically used when maintaining a particular startup and shutdown order for the drives. It's also worth noting that sequence start and stop interlocks are usually not active when the drive is in local mode. This makes sense because during maintenance or inspections, there may be a need to test a single drive in isolation. In such cases, forcing the activation of other drives would defeat the purpose. Now let's proceed with implementing interlocks for our 3 conveyors, ensuring that they start and stop in the correct sequence and maintain the overall system safety. Let's now move to the engineering station and open the FC4003 function, which is responsible for controlling the drive A1G01N03, the last conveyor in the series. Since this drive can start immediately when the group starts, there is no need to add a sequence start interlock in this case. However, we need to prevent a situation where the previous drive, A1G01M02, is still running while we try to stop A1G01M03. To achieve this, the simplest approach is to copy an existing interlock into network 3. Next, we assign a unique index to the MSW pin. Since an INTL interlock with the index W1131 will be created for this drive later in the course, we assign index W1132 to the sequence stop interlock. we connect the link pin of the function to A1G01M_DB.INTLSEQSTP, which links the sequence stop interlock to the drive A1G01M03. For the IN pin, we connect the signal A1G01M02DB.RD1, which is the run delay signal of the drive. This signal becomes active when the drive is turned on and the delay time set in the timer has passed. The negation of this signal indicates that the drive is off. Therefore, our interlock will be fulfilled when the drive A1G01M2 is off. The final step is to connect the negated signal A1G01MDB.look to the ENINTL input, which is responsible for enabling the interlock. This will deactivate the interlock when the drive is in local mode. After this, we save the changes and move on to the FC4002 function. In the FC4002 function, we need to implement two interlocks. The first is a sequence start interlock, which will prevent the drive A1G0102 from starting until the drive A1G01M3 is running. The second is a sequence stop interlock, which will prevent A1G01M02 from stopping while the drive A1G01M01 is still running. After configuring these interlocks, we save the changes. Next, we move to the FC4001 function, where we will add a sequence start interlock to prevent A1G01M01 from starting until A1G01M02 is running. We create the appropriate interlock and save the changes. Finally, we select the three modified functions, FC4001, FC4002, and FC4003, and upload them to the controller. Let's now move to the server and add interlocks to our drives. To do this, we'll go to the point editor. For example, the PLC controller has already created a sequence start interlock for the drive A1G01M01. To add this interlock, right-click on the A1G01M01 drive and select New. Make sure the solution A1 is selected and name the interlock A1G01M1-1. Next, choose the point type as point type ACESYS Interlock INTLSQ-STR8 and set the I/O interface to SIM, then confirm by clicking OK. After that, fill in the description field. This description will be visible to the operator, so it's important to use clear and descriptive names that indicate what the interlock does. In our case, write A1G01M02 is running. This description will indicate that the sequence start interlock for A1G01M01 is fulfilled when the A1G01M02 drive is running. The last step is to configure the I/O interface. Select the controller, S1PLC1, and for the input, enter DB10DW111 bit 0. Once finished, save the changes. Repeat these steps to create additional interlocks for the other drives. Once all the interlocks have been added, let's move to the operator station and press the F5 key to refresh the changes. Next, let's add the connection of tags to the arrows so that they light up green when a specific conveyor is in motion. This will allow the operator to monitor the flow of materials in real time. Click on Edit, then select the arrow and connect the appropriate tag to indicate the material flow. After that, click Edit once again. When prompted to save the changes, click Yes, and you will be redirected to the installation overview. Now let's click on the conveyor. As we can see, a new interlock tab has appeared, where we can check which interlocks are assigned to the given drive and whether they are satisfied. The green color indicates that the interlock is satisfied, while red informs us that it is not. Additionally, a gray color may appear, indicating that the interlock is inactive. In our case, the interlock should not be active when the drive is in local mode. Now let's navigate to the Control tab and click Local to switch the drive to local mode. After changing the mode, a white L symbol appears next to the drive, indicating that the drive is operating in local mode. Returning to the Interlock tab, we see that our interlock is now gray, meaning it has been deactivated and is not involved in controlling the drive. Now let's switch the drive back to automatic mode. Next, we will start the group by clicking Select and then Start. As we can see, even though the group has been started, the drive A1G01M01 did not start, which is due to an unsatisfied sequence start interlock. For the drive to start, the drive A1G01M02 must be turned on first, and the time set in the delay run parameter for the drive A1G01M02 must also elapse. As we can see, the start sequence is working correctly. The drives start in the order: first A1G01M03, then A1G01M02, and finally A1G01M01. Similarly, the shutdown process operates in the same manner. The drive A1G01M03 will not turn off until the drive A1G01M02 has stopped. It is important to note that sequence stop interlocks do not operate during a quick stop command. If we start the group and then select Deselect and click Quick Stop, all drives will stop immediately. The last thing worth testing is how the system reacts if one of the conveyors fails. If an overload occurs on the conveyor A1G01M02, not only will the drive A1G01M02 stop, but also A1G01M01, as its start interlock has been interrupted. However, note that the drive A1G01M03 continues to operate, which is correct since there is no need to stop it in this situation. After acknowledging the alarm, we can restart the group. It's important to discuss the three basic operating modes in which a drive can function in automation. Automatic mode. In automatic mode, starting the drive is associated with simultaneously starting the other drives in the group. Cooperation between the drives occurs in a specified sequence, allowing for harmonized operation of the entire system. A good example of this is the process of starting a group. Once the group is selected, all drives are set to automatic mode, and their start occurs according to the established sequence. Manual mode. Manual mode allows for controlling a single drive from the operator station without the need to engage other devices. This is an ideal solution when we want to focus on one drive without affecting the operation of others. It also enables testing the drive's operation independently from other components in the system. Local mode. Local mode involves controlling the drive using physical buttons located on the device, typically on a local control panel. This mode is particularly useful during maintenance work when we want to verify the correct operation of the drive or check whether it has been properly connected. Let's better illustrate the operation of the drives by activating them in each of the three modes. In automatic mode, a single drive cannot be started. Control occurs at the group level. Thus, enabling the group will result in the activation of all drives contained within it in a specific sequence. When we disable the group and set our drive to manual mode, a blue letter M will appear next to the drive, indicating that the drive is operating in manual mode. This allows us to start the drive directly from the operator station using the buttons on the drive's panel. Pressing the Start button will activate the drive, while the Stop button will halt its operation. In local mode, a white icon with the letter L appears next to the drive, signifying that the drive is functioning locally. To start the drive in this mode, we must simulate pressing the physical buttons that would be located near the drive. By navigating to the Dev Sim tab, we select LSTR1, which represents the signal from the green Start button. As we can see, pressing this button causes the drive to start. Conversely, clicking the LSTP button, which is the red Stop button, will stop the drive. Let's take a closer look at the timers available in the drives and explain how they work. The timers are configured in the Timers tab. Here are some key timers we can set. Delay start. This is the time that passes from when all start conditions are met and a start command is given to the moment the drive is switched on. This timer allows for a delayed start. Return monitoring time defines the time after which an alarm is generated if the drive's contactor has been activated but no A1 feedback signal is received to confirm the activation. Delayed run. This time begins counting after the contactor is activated and the REAT1 signal is received. After this time elapses, the drive sends an active RD1 signal to indicate proper operation. Delayed stop. When all conditions for stopping the drive are met and a stop command is issued, this timer defines the time after which the drive will stop. Start warning determines the duration of warning signals, audible and visual, when the drive is started manually, e.g., in manual mode. It is important to note that the delayed timers only work in automatic mode. Now, let's move to the operator screen and see how this works in practice. Let's temporarily set longer times for the A1G01M02 drive and observe how the system behaves during operation. Pay attention to the fact that when the A1G01M03 drive starts and the interlock is fulfilled, the A1G01M02 drive doesn't start immediately. This happens because the interlock of the A1G01M02 drive is linked to the RD1 signal from the A1G01M03 drive. This means that after A1G01M03 is switched on, the delayed runtime for this drive must pass before the interlock of the A1G01M02 drive is satisfied. However, satisfying the interlock does not immediately start the drive. Once the interlock is satisfied, the delay start timer begins counting, and once it finishes, the drive's contactor is engaged. When we receive confirmation of the contactor's activation, rate 1, the delayed runtime is counted. Only after this time passes is the interlock for drive A1G01M01 fulfilled. Let's do a brief summary of the available options and tabs in the drive faceplate. Control allows you to send start and stop signals to the drive and change its operating modes. Interlock lets you check which interlocks are assigned to the drive and whether they are met or blocking its operation. Input displays the status of the physical inputs assigned to the drive. Output shows the status of the drive's output signals. Timers enables the configuration of time parameters related to the drive's operation. Motion settings for motion control of the drive. You can configure two types of motion control, continuous input or pulsed. Point para allows you to configure alarm suppression settings. DevSim used to simulate the drive's inputs. Config. In this tab, you can select the drive type, configure alarm transmission methods, add features like a motion detector or an additional button to the faceplate, and set the modes in which sound and light signals should operate. You can also enable drive operating modes and, if the drive supports analog measurements, add the analog tab for monitoring those signals. You can also configure which inputs are visible in the Input tab. Info allows you to define parameters such as the dB data block associated with the specific point for the drive. Drive parameters configured through the faceplate are saved in the data blocks associated with that specific drive. However, it's important to note that these changes only affect the actual values in the data block of the simulated controller. This means that if the controller is running in simulation mode, the changes won't be automatically saved in the offline data blocks. When you disable the simulation and reload the controller, the offline blocks, which haven't been updated, will be loaded into the controller, and this could result in losing the configured settings. To prevent this, it's a good practice to manually copy the data blocks from online to offline once your configuration is finalized. To perform this operation, follow these steps. Go to the engineering station and connect to the system in online mode. In online mode, select the blocks that were modified, in our case, D1501, DB4001, DB4002, DB4003, while holding Control. Right-click on the selected blocks and choose Copy. Then switch to offline mode and paste the copied blocks. This will ensure that your configuration is safeguarded from being lost, and when you reload the controller, all the settings will be the same as they were when the blocks were copied. This simple but crucial step ensures that changes made online are permanently saved. Let's proceed with adding two alarms to the PLC controller program. The first alarm will monitor the overfill of Silo 1 and will be named A1G01AL1 level, while the second one will monitor the level in Silo 2 and will be named A1G01AO2 level. The process of adding these alarms is similar to the process of adding Unimotors. First, locate the FC2001 block, right-click on it, and select Object Properties. Change the symbolic name to A1G01AL Level FC, and in the comment field, enter Overfill Silo 1 Alarm, indicating that this is an overfill alarm for Silo 1. Then locate block DB2001 and rename it to A1G01AL1 Level DB. Next, enter the FC21 function, where we also set the name to A1G01AL1 level and add the comment Overfill Silo 1. Alarms are simple functional blocks that have several inputs. The first one, SIG, corresponds to the signal that triggers the alarm. In our case, this will be a signal from the overfill sensor mounted on the silo, connected to the physical input of the controller at address I0.0. A logical value of 1 means the silo level is not exceeded, so the alarm is not activated. The PBR input indicates the power status of the sensor. In our case, this signal will come from input I0.1 on the controller's card. The ENL and ENH inputs define which state will trigger the alarm. In our case, a low state, logical 0, is the alarm state, so we set ENL to 1 and ENH to 0. The AL super input is responsible for alarm suppression. Since we do not want to suppress alarms, we set this input to 0. If we set it to 1, the alarms would not appear on the alarm list. Next, we properly connect the token input. Since this alarm belongs to the A1G01 group, we connect the token for this group. Similar to other objects, the alarm sends a status word, so a unique index must be assigned to the MSW output. The statuses of all alarms are stored in DB6, where there is a table of alarm status structures. We create the second alarm, A1G01AL2 level FC, analogously. This alarm will use two physical signals, I0.2 for the overfill signal and I0.3 for sensor power control. After adding both alarms, we move on to their simulation, which is carried out in FC7992. We will simulate the SIG and PWR signals for both alarms. Open this function, change its name appropriately, and connect the physical inputs so that they can be simulated from the ECS system. Once the alarms are added to the simulation, they need to be invoked. Both alarms belong to the A1G01 group, so we enter FC1501 and invoke the alarms using the call FC2001 and call FC2002 commands. The final step is to load the changes into the controller. To do this, select the modified blocks while holding down the Control key. In this case, the blocks are FC1501, FC2001, FC2002, DB2001, DB2002, and FC7992. Then click the Load button to load the controller. The next step is to add the appropriate points on the server. To do this, open Point Configurator, right-click on the A1G01 group, and make sure the correct solution is selected. Name the alarm A1G01 ALL01 level. Select Point Type as Point Type ACESYS Alarm 8.0 and choose I/O Interface as SIM. Click on the added alarm, enter Overfill for Silo 1 in the description field, and select the controller S1PLC1. Then fill in the I/O interface according to the address table shown in the course. Input DB, 32-bit time, DB6 DW6-bit 0, output DB, 16-bit, DB2001D 26-bit 0, parameter, DB2001 DW0. Click the Save button. The second alarm can be created by copying the first one. Right-click on the A1G01AL1 level alarm, choose Copy, rename it to A1G01AO2 core level, change the description to Overfill for Silo 2, select the S1PLC1 controller, and adjust the I/O interface accordingly. Then save the changes. Since new points were added, refresh the changes by pressing the F5 key. Now, go to the HMI editor, open the S1A1 EMRO1 screen, and use the tag browser to drag the added alarms onto Silo 1 and Silo 2. To position the alarms more precisely, you can reduce the grid size. Overfill alarms are typically labeled with the letter L for level, so change the type indication property of the alarm to L. Save the changes and go to Preview mode. You should now see that both alarms have been correctly added. By clicking on the DevSim tab, you can simulate the alarms. For example, turning off the SIG signal will cause the alarm to light up red. In automation, there are standards that define what each letter in alarm codes represents. The key types of alarms include L level, overfill alarm, T, temperature, overheating alarm, P, pressure, pressure alarm, F, flow, flow alarm, X, error, device error alarm, S, safety, safety alarm. Similar to Unimotor motors, alarms have delay times that allow control over the time before the alarm is activated or before a warning or alarm is generated. Enable delay, the time after which the alarm will be activated once a signal of 1 is received on the ENL or ENH input. Warning delay, the time that must pass before a warning is generated. Alarm delay, the time that must pass before an alarm is triggered. Now, let's move to the server and examine the contents of the alarm faceplate. In the Control tab, we can monitor the inputs and outputs of the function blocks, FB, associated with the alarm. The Parameter tab allows setting delay times for alarms and warnings. Additionally, in the Force tab, it is possible to manually force alarms. In the Point Para tab, you can activate the alarm suppression function. DevSim allows for simulating alarm signals, which is helpful in testing the system. In the Config tab, you can configure whether a specific alarm should be treated as a warning, an alarm, or both. For example, if an undesired state persists for longer than a specified time, you can trigger an alarm instead of a warning. It's important to note that a warning does not change the output state of the OK alarm. You can also configure cyclic alarm repetition by selecting the Enable Repeat Alarm option. In the Config tab, you can also manage alarm suppression. If the Suppressed by Parent Group option is selected and the group is inactive, the alarm will not display in red, but in orange, and will be sent to the alarm list. When the group is activated, the alarm will turn red and appear in the main alarm list. In the Info tab, you can see which data block DB is associated with a particular alarm. This is crucial for system analysis and diagnostics. In our project, we must prevent the conveyor A1, G01, and 3 from starting when the overfill alarm for silo 1 is active. This is a hazardous situation, so an interlock should be applied, which will immediately stop the entire group when the alarm is triggered. This approach enhances system safety and protects against potential failures. Let's move to the engineering station and add an additional interlock. First, navigate to function FC4003. The interlock will be named Silo 2 is not overfill. Start by copying the previously created interlock and modifying it. This time, set the EN-INL input to always be on, since this interlock needs to be active at all times. For the IN input, connect the signal indicating that the Silo 2 overfill alarm is inactive, which is A1G01AL level.OK. This will be a simple interlock, INTL. Assign its status index 1len31. Save the changes and upload the modified function. Next, move to the server. Open the point editor and add this new interlock as A01M3 INTL1. Set the interlock type to point type ACESYS Interlock 8.0. For the I/O interface, select SIM. In the description field, enter Silo 2 is not overfill. Select S1PLC1 as the controller and set the input to DB10D1131. Save the changes, press F5 to refresh, and move to the overview to activate the group. Click Select, then Start Group. Once the group is running, let's trigger an overfill alarm for Silo 2. Click on the alarm, navigate to the DevSim tab, and set SIG to 0. As you can see, the entire group immediately stopped. Note that while the alarm remains active, the group cannot be restarted. It's important to remember that an interlock that is not a sequence interlock will stop the group. In many interlocks, we often use conditions derived from other points. A good practice in creating effective visualizations is to provide operators with tools that allow them to quickly diagnose system issues. When it comes to interlocks, one helpful feature is adding a related point. This allows operators to view the statuses of points and open the faceplates of points related to the interlock. Let's take a closer look at this by going into the point editor. For example, the drive A1G01M01 has an interlock connected to the startup of the drive A1G01M2. This means that the startup procedure for A1G01M01 is dependent on the status of A1G01M02. Therefore, the interlock should have A1G01M2 as a related point. We will now create related points for other interlocks and observe how this improves the visualization. After saving the changes, we move to the operator station. Now, when we enter the Interlocks tab, we can see the status of the related point on the right side of the screen. Let's start the group and see how much more readable this setup is for the operator. It becomes immediately clear which interlock is blocking the drive from starting and the status of the equipment associated with that interlock. Another useful feature is that we can open the faceplate of the related drive directly from the interlock screen without having to search for it on the plant diagram. This is especially important in large systems where there may be thousands of points to navigate through. By implementing related points, operators can quickly understand the cause of the issue and access the necessary information without delay, making the system far more user-friendly and efficient to operate. To add 2 analog sensors for silo fill level measurement, we begin at the engineering station. Open the hardware configuration of the controller, select S1PLC1, and navigate to the hardware section. Notice that the ET200IO module is configured with 8 analog inputs on slot 10, occupying addresses from IW500 to IW515. Each analog input occupies 2 bytes or 1 word. Select the input module, go to the Inputs tab, and verify that each input is set to the 420 mA standard, which allows long-distance signal transmission and enables monitoring of circuit breaks or short circuits. After configuring the hardware, proceed to the symbol table, where 2 analog inputs have been defined, IW500 for Silo 1 level and IW502 for Silo 2 level. Then open function FC301, rename it to A1G01AN1 level FC, and update its description to Fill Level in Silo 1. Similarly, change the name of DB301 to A1G01AN01 level DB. Inside FC3001, add comments to keep the code organized. In Siemens standards, the range of analog input values is from 0 to 27648. To handle this, first convert the ID500 value to the real type, then scale it to a range of 0 to 100 using the scale function. This scaled value is then input into block FB204. It's important to set the parameter SIG-type to 0, indicating that the function block expects a normalized value in the 0-100 range. Diagnostics for analog measurement errors is essential, as 2 common fault conditions can occur: wire break and short circuit. If the current falls below 4 mA, the dummy real value becomes negative. When the current drops below 1.1185 mA, value -4864, the input U range switches to 0, triggering an open-loop alarm in the ECS system. Similarly, if the current exceeds 22.1 mA, value 322511, the O range input switches to 0, generating a short circuit alarm. This enables quick diagnosis of analog measurement faults. To add the second analog measurement, first copy FC301 and save it as FC3002, updating its name and description accordingly. Next, copy DB3001 to create DB3002 and adjust the block name. In FC3002, replace all instances of IW500 with IW502 to reference the second measurement. You can use the shortcut Ctrl F to quickly find and replace all relevant occurrences within the function. Additionally, adjust the MSW status index to 2 to avoid conflicts. Remember to simulate the analog measurements. For this, go to function FC7991 and rename the network to A1G01AN score level. Assign the analog input address IB500 to PV-RAW so the analog value can be simulated in the ECS system. Copy network 1, rename it, and assign IW502 to PV-RAW for the second input, also updating the reference to A1G0102 level D.FPSim for simulation. Save the modified FC7991 function. Finally, open function FC501 and call FC301 and FC3002 using the call commands. To apply the new settings to the controller, load the modified functions F1501, FC301, FC3002, as well as data blocks DB301, DB3002, and FC7991 into the PLC controller. The next step is adding these measurements to the ECS system. Go to the System tab, open the point editor, and within the A1G01 group, add 2 analog measurements. Name the first one A1G01AN01 level, set the point type to point type ACESYS analog in all 8.0, select the I/O interface as SIM, and add the description fill level in silo 1. In the analog settings, choose engineering units as %, assuming the sensor reads tank fill level from 0 to 100%, and set decimal places to 1 for a display accurate to 1 decimal point. In the I/O interface tab, assign the controller as S1PLC1, then map the input to DB7 D14 bit T0, output to DB3000 D44, and parameter to DB3001 DW0. Save the changes. To add a second analog measurement, duplicate the first one, rename it A1G01AN score level, and adjust the I/O interface to match the correct PLC address space. Save the settings and refresh the configuration with F5. Once the analog points are set, you can display them visually. Open the HMI editor and load the existing screen. Drag the analog tag from the tag browser onto the screen, setting properties like unit width to 20, font size to 16, and font size unit to 12 for optimal appearance. Position this measurement on silo 1. Next, open the toolbox, find the fill bar object under the Dynamics tab, and drag it onto the screen. Set its background to gray and link it to the analog measurement by copying the tag name to the fill bar. Adjust the elements for a clean appearance on silo 1. Finally, copy these elements and place them on silo 2, updating the tag reference to the second analog point. Save the changes and click Preview to review the visual display. This way, we successfully added 2 analog measurements to our visualization. Let's double-click on the newly created analog measurement, which automatically opens the configuration window. In the Main tab, you'll see a graphical bar showing the measurement scaling and the threshold set for this measurement. The Trend tab displays the measurement changes over time, and in the Control Limits tab, you can set alarm limits. In our case, it's useful to set these limits to prevent the group from starting when the level in silo 1 is too low. Let's configure the alarm thresholds as follows. L3 fatal alarm, 0%, L2 alarm, 10%, L1 warning, 20 H1 warning, 80%, H2 alarm, 90%, H3 fatal alarm, 100%. Let's also add a small delay of 1 second for each alarm to filter out any measurement noise and set the alarm off hysteresis at 1%, which will allow the alarm to be cleared only when the value drops 1% below the threshold that triggered it. You can also configure control limits. Note that for alarms and warnings, a value of 1 signals a normal state when the measurement is within limits. For control limits, however, it's the opposite. A state of 1 is triggered when a level is exceeded. In the Scale tab, you can configure the measurement scale, and in the Treat tab, you can set delays for underrange and overrange errors. The damping parameter determines how long it takes for the measurement to stabilize at the target value after a change. For instance, if we simulate a value change from 70% to 85%, the change will take 5 seconds. In the Input tab, you can monitor the function block's inputs, while the Output tab shows the outputs. The Point Para tab enables alarm suppression, and the Point Limits sub-tab allows setting additional internal alarms for display purposes only, which don't affect block outputs. You can also adjust gain and offset for the measurement and set the maximum value for the analog signal. The DevSim tab lets you simulate sensor values, while the Configuration tab includes settings for enabling alarms and the option to mute them, for example, at the group level. Lastly, the Info tab shows which function block handles this analog measurement. Now, let's configure the second analog measurement in the same way. To save the configuration, the easiest method is to copy the data blocks from online to offline, so the settings are retained in the next controller upload. To do this, go to the engineering station and copy the DB3001 and DB3002 blocks from online to offline. Finally, let's create two interlocks for these analog measurements to immediately stop the group if silo 1 reaches the L2 alarm threshold, almost empty, or if silo 2 reaches the H2 alarm threshold, overfilled. Go to function FC1501 and add these two interlocks. Name the first interlock silo 1 is not empty. Go to block FC3001. Copy the output A1G01AN1 level db.ALL2I and paste it to the input of the interlock. Copy network 1, name the second interlock silo 2 is not overfill, and connect its IN input to A1G01AN02 level db.LH2. Upload the functions and go to the ECS system to add these two interlocks. Name the first interlock A1GINTL1, select point type as point type ACESYS Interlock ammo, and set the I/O interface to SIM. Name it silo 1 is not empty. Select controller S1PLC1 and assign it the address DB10DW1101 bit 0. Configure the second interlock similarly, adjusting its name and I/O interface as needed. Save the changes, refresh the view with F5, and go to the Product Operations Station tab to see the setup. Finally, let's simulate what happens if the level in Silo 1 drops below 10%. We expect the group to stop immediately. As you can see, everything worked correctly. The group stopped as expected. Let's also check how the group behaves in the second scenario, where Silo 2 reaches its maximum level. As expected, in this case as well, the group immediately stops, meeting our requirements. That's all for this session. Thank you for making it to the end. I know we covered a lot of new concepts related to the ECS system, but this practical knowledge will enable you to independently design simple automation setups using ECS. However, the information presented here is just the beginning. ECS has many other features worth exploring, such as PID controllers, selectors, totalizers, gates, valves, and blocks for communication with other PLC. If this topic interests you and you'd like to access more video materials, along with virtual machines to practice and test your automation setups, feel free to reach out to us at automationmindsinfo@gmail.com. See you in the next lesson.